To lecture 8 of the course. And in this lecture, we're going to touch on something that is rather fundamental. And it has to do with the implication of fluctuations and dissipation on the notion of reversibility of a system. To try to give some context, we have a simple concept of time reversal in any closed system. If the Hamiltonian or the Lagrangian of the theory is left invariant by a Z2 type of transformation, Z2 being the group being made by two elements, that just flips the time forward into backwards and vice versa, then your theory is invariant. That means that the equations of motions are the same, and therefore that you can equally good solution going forward in time and backward in time. And that's it. And there's no more concept to it if you want. When we deal with an open system, we are led to thinking that the time arrow is actually broken, and that's actually a fact, because we know that we have a specific line in the arrow manifold associated with the growth of entropy. And therefore, you can tell, we had this discussion at the beginning of the course, when two events have been happening in one order or in another. Think about lighting a match and watch it burn out. Obviously, the last picture you take of the match being completely burnt out comes after the first one, in which you still haven't lit it. Yet it so happens that some concept associated with reversibility must survive even in an open context. How do we know? Well, when we took our thermodynamics course at the beginning of our physics education, we had this notion of reversible thermodynamic transformations. You have, your piston moving extremely slowly, and somehow that reversible concept was implying the fact that the entropy was not changing during the transition. The total entropy was unchanged of the path plus the system during a reversible transformation. Of course, either the system or the path could change their entropy depending on the kind of transformation, but the sum, the total balance was supposed to be zero. So there was some kind of concept of reversibility tightly linked to the concept of entropy production that somehow survives even when you deal with complex open systems. But that was as much as we probably all went in our education till this point in digging into the implications of this. So, because you see, after that, you rediscover thermodynamics in the eyes of statistical mechanics typically on the third year, at least in Italy, of college education. And you discover that you can define entropy for ensembles, and all the principles of thermodynamics are actually consequences of Hamilton's equations in last instance. Yet this idea of something going on and being reversible remains somewhat abstract. And even the concept of entropy production is, to me, quite elusive in thermodynamics and in statistical mechanics of equilibrium system, simply because there is no time in those descriptions. And if there is no time, what can you tell what is the rate of entropy production if there is no time scale? So in some sense, you sort of limit yourself to notice that in some equilibrium state there is more entropy than in some other, and you completely lose information how this entropy is actually being produced during the process. But the formalism we developed over the last several lectures enables us to finally touch onto fundamental questions and sort of make sense of the principles of thermodynamics, not only in the framework of purely equilibrium systems, but more generally in the framework on non-equilibrium conditions. And that's one of the, so if you want, most striking implications of whatever we've done so far. rederiving thermodynamics in a deeper sense, so to say, and in a dynamical sense. So what we're going to do today is to touch on several aspects of thermodynamics from the Langevin point of view. We already touched on principle zero of thermodynamics. Remember, the zeroth principle of thermodynamics, which is very rarely quoted as a principle, but it's basically a principle that you have to state at the beginning of your thermodynamics course when you say, take two bodies, I put in contact, and whatever is temperature after a while is the same for both bodies. Although you don't know what temperature is at the level of first year, you say temperature is whatever my thermometer measures. But I observe that when I put two bodies which have different temperatures and put them in contact, after a while they reach the same contact. Now, in the context of Langevin, that simply implies thermalization. And in fact, we demonstrated that if you take your particle, your system, and you put it in the bath of a harmonic oscillator that you integrate out, so in a stochastic environment, then the Langevin equation's properties and symmetries imply that in the long time limit, the solution of the Fokker-Planck equation is the static solution, the zero modes, and it's the Boltzmann distribution. So basically, we've demonstrated principle zero of thermodynamics, at least within the context of Langevin dynamics. And now we're left with two more principles, right? Principle one, and principle two. Now, principle one and principle two, it's where the action starts going. Actually, principle one is sort of trivial still, because we have built Langevin dynamics out of a Hamiltonian descriptions of a closed system. So in our original description, energy was conserved because the Hamiltonian was, of course, an integral motion for the full system plus path system. And since principle one is nothing but a balance of energy and reflects energy conservation, we certainly expect energy to be conserved once we take into account the energy exchange between the bath and the particle, and we sum up all the contributions. Nevertheless, it's instructive to do that because we'll discover the concept of heat at the microscopic level. Principle two has to do with entropy production, and that's where really the discussion will become more interesting, and it's actually quite active fields of research these days for reasons that I will comment on later on in the course. So let's go over principle one of thermodynamics for 1 second. And the way we do that is by starting with the Langevin equation once again. And I'm going to write it this way. I'm pulling off this factor, assuming this as a unitary variance up to a factor delta t, which enters in the definition of the delta functions, essentially. And it's a convenient way of writing this, but it's not the only one. And for sake of simplicity, I'm assuming this equation holds in the Stratonovich calculus. In the Stratonovich way. Which means that whenever I will have to do path integrals and compute integrals, I will use the fundamental theorem of calculus as is. And, I don't need to worry about weird properties of stochastic calculus. Okay, so let's imagine now, let's follow the dynamics for a time delta t. And the system performs a displacement delta x. Now, we want to measure the heat which is exchanged between the particle and the environment. Well, the particle exchanges energy with the environment essentially through viscosity and through random forces. So the two ingredients that really are responsible for the balance of energy with the heat bath are these two terms. The first derivative, remember, is associated with the viscosity of the particle, the acceleration being dumped out in this formulation already. And the last term is precisely the random kicks that a particle gets from the environment. So they are the terms responsible for heat. So if I were to define heat in this system, exchange over a time delta t, I would say have an incremental heat that gets exchanged at time t, and that's minus m gamma x dot plus root of 2 kt m gamma psi of t. Times dx. Why? Because this is the force responsible for exchanging energy with the environment, and this is a work made by those forces by taking the inner product with the displacement. That's simply energy exchanged with the bath. As simple as that. But then I can use the Langevin equation here and relate these terms to the force, to the conservative force of the particle. So I would be tempted, actually it is correct if this is the kind of setting we have to write that this is nothing but du of x dx of t. So that's the definition of heat exchange, and it's related to the work of the conservative force because of the Langevin equation. Now we want to be a little bit more general now. I'm letting the potential energy that enters this equation to depend explicitly on time, not only on time through the position of the particle x. What does it mean in physics? It means that I'm letting the system to be controlled by externally, and therefore to have an external work pumped into the system. If this is not clear, you can think of two possible examples. In one example, you imagine a collection of electric particles, say electrolytes, they are positive and negative particles, a plasma in equilibrium, and they have their own stochastic motion. At some point, you switch an electric field with a certain schedule. You switch it on with a given time frame. And it's like if you're exerting stronger and stronger forces that pulls apart the positive and negative charges. Now, if you do that, then clearly all the dynamics is changed, and you are modifying the internal energy of the system because it costs energy to induce that electric field, and that energy is transferred onto your system and heat bath by the dynamics of the system with a heat bath. So in other words, you got to pay an electricity bill to perform these experiments at the end of it. Therefore, you expect that the heat exchange in this general context will reflect itself into some kind of work and change of internal energy, and we're going to compute that. Before we make this calculation, let's also consider a second example, which is very, very, very much fashionable in the last decade. And instead of a biophysical experiment in which you, for instance, have a polymer, for instance, take a protein that is somehow formed in its native state, and then people are attaching covalently bound DNA handles at the side of it. And right here, at the end of the DNA bundle, they take an iron ball, a gold ball, typically. And then they put this in optical tweezer and they pull. They could exert piconewton type of forces, and by doing this, they can monitor how this force induces the unfolding of the protein. And this is clearly a system in which you're pumping energy and work into the system and watching the consequences. Okay, so in more general sense, the change of internal energy, if the potential depends also explicitly in time, will be given by the work, now with explicit time dependence, plus a new term which you can express in the following way. Because this is really the power, this is the power of energy associated with the energy pumped into the system by the external equipment multiplied by the time, and it will give you the total work. So that's the work, and that's the heat. And therefore, this expression here is nothing but the first principle of thermodynamics, right there, but in an explicitly time-dependent manner. So this equation holds true at every instant in time. Now that's an amazing statement because the system is open, but we are basically keeping track of the flow of energy in this open system. Okay, that's as much as I wanted to say about the first principle of thermodynamics. And for the sake of the rest of this lecture, let's just bear in mind this important relationship that we worked out before. Now I'm restoring the vector components as to highlighted. This will become handy in a couple of minutes. Now let's talk about the second principle of thermodynamics, entropy production. And remember, we want to explore whether some concept of reversibility can still take place in an open system with dissipation. So what would be a reversible process? Now there's no determinism anymore. There's no equation of motion left invariant. The only thing that can be left invariant, if you want, is the probability of observing one path in one direction from x initial to x final. So the probability of generating a path, now I drew the path in a smooth way. I should have not drawn it smooth. I should have drawn a stochastic path because remember we are in the framework of stochastic dynamics. The probability of a path x of tau such that x of 0 is equal to xi and x of, say, t is equal to xf. And we want to compare the probability of this path with the probability of its reverse path. What its reverse path is a path x bar, which is actually x of t minus tau, and it has the opposite boundary condition. X bar at 0 is equal to x final, and x bar at t is equal to x initial. In addition, we want to reverse any external protocol acting on the system. To be more specific, if we were switching on in time t in a homogeneous way the electric field, now we imagine to switch it off while we go back. So really, we want to reverse anything that can be time reversed. And then we have and then we ask, in this setting, what are the relative probabilities of observing the same path, but just in a reverse time order? That's the question associated with reversibility of a stochastic process, really. That's what reversibility of a stochastic process, even wordy, should mean. But we have developed the right tools to address this question when we developed the path integral formulation of stochastic dynamics, because you see, the path integral formulation of stochastic dynamics is in fact a way of establishing the probability of a path and then summing over all paths, each one with its own probability. So we can address this question using what we have studied so far. So what we do, we compute the probability of path x, condition to start from the point x naught. So that's the functional probability of a path x of tau, condition to the initial point of the path, x naught is x of t equal naught, and that's x initial, if you remember. And then we divide by the probability of the reversed path, condition to the point x bar naught. And the x bar naught is x bar at time naught, and that's x final. Now, the path integral formulations that we developed tells us that this is just a relation of Onsager-Mach group exponents, right? So if you do that, that's really like e to the minus s Onsager-Mach loop of the path x divided by e to the negative of s Onsager-Mach loop of the path x bar. Now, if you take the Onsager-Mach loop action and write it up explicitly and discretize it in your form, either you do it in Ito form and then you account for the Laplacian term, or you do it directly in the Stratonowicz form, it's quite straightforward to reach the conclusion that this ratio of probabilities that you have here is in fact e to the negative, actually positive, 1 over t d tau x dot grad u of x and t. That's kt here. Now, if you reverse it, sometimes in the literature you find this equality in the reversed order, when you measure the probability of the reverse path relative to that of the forward path. But the important thing is this is evaluating the forward path. Okay, so the two paths are clearly not equally probable, but it's quite clear from the discussion that we have that the amount of violation of reversibility is actually controlled by the heat. So you can rewrite all this. Now I'm gonna switch back to the more kosher relationship. I'm inverting the probability. The probability of the reverse path divided by the probability of the forward path is written as e to the negative 1 over kt, and then I have delta q, right? Integrated over time. So basically, what you have here is something which you can write in the following way. And therefore it's an entropy change. Why is it an entropy change? Well, first of all, because this is delta Q over T, and we know from first year that delta Q over T is an entropy change. And also, we see clearly now how the entropy change breaks the possibility of reversing the path in one direction or in another. So there's something associated with entropy change that affects the probability of processes to occur in one direction relative to the opposite. And that resonates with our basic general thermodynamics understanding that entropy variations are enemies to reversibility, but in a much more microscopic way. Now, everything is said so far is probably kind of making sense, but we have not been very, very accurate in deciding what kind of entropy we're talking about. And if you think about it, this is the entropy of the bath, because what we looked at is the energy exchange with the bath and related to temperature. But as we move forward, we also have in time during this transition, there's also an entropy change associated with the state of the particle. And if we want to make a statement about global entropy production and reversibility, we need to be taking into account of that also. So, if I look at it, what is the entropy of a particle? Well, the entropy of a particle, which I call the system, at x and t, can be constructed from the distribution and configuration space. Remember, this is basically equivalent to writing that the entropy is rho log rho. But that means that this is the density distribution over which we are computing an average, and this is the quantity that you're averaging, right? So, based on this, you would call the entropy here minus k log p of x of t, where this is the solution of the Fokker-Planck equation. Plays the role of rho at equilibrium and has an explicit time dependency. So the change of entropy in the system is actually negative kb log Now, with all this in mind, we are actually ready to define what is a microscopically reversible system. Well, a microscopically reversible system is one in which the total entropy change is zero. And if I go back on my previous equation, p bar over p equals to e to the negative 1 over t. Now let's take a situation in which I'm not pulling in energy into the system for a moment. I leave the system as such, I leave it in equilibrium, and then my particle is just moving. These dynamics of the particle, since I'm not perturbing the system, it's just a microscopic dynamics, this should be reversible. And therefore, if this is just delta U, remember we are now not explicitly depending on time, and since we are working in the framework of Stoyanovich calculus, we can apply the fundamental theorem of calculus, and we get that the probability of the forward process, the backward process, given the equilibrium distribution of the final particle, which is the initial transition of the backward process, remember x final, x initial, is equal to the probability of the forward path given the equilibrium distribution of the forward process. Now, if you exponentiate these two equilibrium probability, they will produce the entropy change of the particle. So the equal probability of the two paths is directly related to the null total entropy variation, which is exactly what you would expect from thermodynamics. It's quite fair, quite nice, isn't it? This relationship here looks like the detailed balance condition. But it's not the detailed balance condition. I will define the detailed balance condition for those who haven't heard of it in a minute. I just want to say it's a statement about initial conditions and paths. not about probability of events. We did not mention the probability of going from xi to xf. We mentioned the probability to go from xi to xf along the path x, or x bar. But if we integrate over all paths that go from xi and xf, we get a path integral, which is in fact is the transition probability at time t from the initial to final configuration. So after integrating over all forward and backward path, in other words, on the left hand side and back and right hand side I perform the path integral, we obtain that the equilibrium distribution times the Fokker-Planck probability to go from the initial distribution to the final distribution time t, let me write it in a more readable way, is equal to final and the probability to go from the final to the initial. So we see that microscopic reversibility is closely related to detail balance. Sometimes in the literature they are treated as synonymous. They almost are synonymous, but the microscopic reversibility is rather a statement about the probability of a path, while the detail balance condition is more a probability of transition, a relationship between transition probabilities and equilibrium distribution. Okay, I think this is quite all of it. I want just to emphasize that everything that we've said so anything new that we said was to show how this path reversibility is connected with entropy production. And there's quite a strong activity in understanding now this process in non-equilibrium process. So now violating this idea of letting the system be in contact only with the path, but let the system be driven out of equilibrium and monitor what are the physical implications of it. Okay, you can think about driving a system externally, like in the example that I was interested in. I was explaining you before, the example associated with pooling a protein, for instance. Or you can think about the system being driven out of equilibrium by itself. Think about a bacterium, which burns ATP and use this energy, chemical energy, to move his flagella and swim. Now you have a Brownian motion that is burning energy to go. And this is called active Brownian particle. And there's quite an activity in understanding what kind of properties remain when you break microscopic reversibility, and what happens to thermodynamics when the system is constantly driven out of equilibrium, either by active agents or by external agents. And I think this is a very interesting subject, and we might be digging a little bit into it in the context of Crookes theorems later on in the course. I'll see how much time do I have at the end of the course, whether I want to throw this into the lectures or not. For the time being, I think I'm done, and see you next time.